Welcome to this discussion, which is hosted by LENRforum.com and is in the control of artist and author Ruby Carrot, who's recording this discussion with Dr. Edmund Storms, formerly of Los Angeles National Labs. I think I've got that right, or Los Alamos National Labs, sorry. And also a pioneer in many ways of many aspects of the cold fusion business. And he's been at the game for many decades, and is an incredible source of information, and has yet to stop coming up with new ideas. You can see something about Ed's work on the conference website from ICCF 24, where there's a recording of this presentation on YouTube, and his latest paper is available at lenr.org. I think the last and perhaps in some ways very important thing I should mention is that I had the pleasure of being alongside Ed at ICF and Ruby at ICCF 24 when he was presented with the Toyota Gold Medal in recognition of his work in the field. So without further ado, I'll hand over to Ed, and there are many things we want to talk about today, Ed. But first of all, I follow your comments in the Google group and so on. About maybe a year ago, you suddenly sort of appeared to switch on to a whole new sequence of events in LENR. I know it was based on your previous work. Of course, everything is, everything we do in the lab is a rehearsal for what we're going to do tomorrow. But you appear to have achieved some kind of a breakthrough in reproducible LENR. Could you tell us a little bit about the current state of that and what your feelings about it?
Well, yes, I have been looking at this field for now over 30 years. And normally when you have success, it's pretty accidental. It requires getting a piece of palladium that, for reasons at least previously were unknown, made energy. Ordinary palladium does not make any energy. And of course, that's what the skeptics focus on. But if you have palladium that has a suitable, what I call it, characteristic, you can make excess energy every single time. My effort has been to try to identify what was unique about the palladium that made it possible to be activated. And over the years, I've tried various ideas. Some worked and some didn't until recently. And that recent success has given me confidence that maybe I'm on the right track. And that's what stimulated my comments on the discussion group. Also, I've become more understanding of the mechanism. And that mechanism is fairly straightforward and is totally consistent with what's observed. And so that understanding gave me confidence. As a result, I've been trying to encourage people to go down the same path that I've been going down. Most people are not going down that path, and I think that the path they're going down leads to a cliff or leads to inaccessible success. My success now has been fairly constant, which has allowed me to be much more confident that maybe I'm on the right path.
Well, Ed, let me ask you about the materials aspect, because one of your breakthroughs was about the materials. Talk about what did you discover that allowed you to make this new formula of active material?
Well, I understand the answer. You need to go back a little bit to the logic that on which this idea is based. The we've found over many years and many occasions that special palladium worked and ordinary palladium did not. And the special palladium that worked, it did not matter what its configuration. It could be a plate, it could be a wire, it could be a rod. And it would work routinely. Occasionally I'd get a piece of this and it would work. Early in the field, Takahashi had a piece of palladium made. All members of that batch, and this was a sheet, were found to be active. And he sent me a sample and I found it to be active. He sent it to other people and found it to be active. And that also was a clue that it's batch dependent. Something about the initial material in the batch that is made by the manufacturer makes the material active. It's not something you do later on, although you can activate it in other ways, but that particular activation was very predictable. The question was, what did the manufacturer put in the sample that would later make it active? And that took a little bit of reasoning to figure out. And it occurred to me that in the process of purifying the palladium, small particles of oxide would have been suspended in the melt. And in fact, as Fleischmann even said, that the Johnson and Matthey purified their palladium by adding calcium boride. And the supposition was that the boron and the calcium would react with the oxygen. Well, the boron would form a liquid at those temperatures, forming the boron oxide. But the calcium oxide would have formed small particles. And these small particles would float to the surface, but many of them would not. And my supposition was, well, what would happen if some of these particles remained in the sample? Well, if that happened and the sample were then loaded with deuterium, the loading process causes the sample to expand, but the region, the calcium oxide, would not react with the deuterium and it would not expand. So a gap would form between the calcium oxide particle and the palladium. Suppose the nuclear reaction occurred in that gap. Suppose that gap was necessary to allow a structure to form between the hydrogens that would subsequently allow the fusion reaction to take place, because it obviously could not take place within the crystal structure itself. Well, okay, so let's put some calcium oxide in. And I tried that using different techniques. And finally, the technique that seems to work quite nicely is to put calcium oxide on the surface of a piece of palladium and then melt it, causing the calcium oxide to be suspended within the sample. And I found that calcium oxide having large particle size did not work. Calcium oxide that had a small particle size did work, and it works routinely. Mm-hmm. So, and it isn't just calcium oxide. It turns out that any high melting material, boron nitride even works, will activate the palladium if it's in the palladium as fine particles.
If I can make a comment, Ed, two of my family worked at the Harlow Metal Company, which was who supplied. They were actually taken over by JM in the late 80s, I think. And the way they used to smelt the palladium was exactly as you described. They used boron calcium boride flux, but a lot of the palladium that was made there was actually made from old jewelry and medals and palladium coins and so on. It was all remelt stuff. and they didn't actually purify any palladium ore or anything like that. So it was mostly scrap derived from the 1,000 or so pawn shops that existed across the UK. So, and the forge master, as he was called, the guy who used to load the furnace, or the crucible that they melted it in, he mainly depended on his eye to determine what was palladium and what was not. And they'd have wooden ammo, old ammo crates full of scrap, and he would be there throwing stuff in that he liked the look of and discarding a few parts. But it had things like jewellery mounts in there, which are plated with rhodium. Yeah, and the rhodium is much higher melting point. It would sink to the bottom, of course. But it really was a bit of a sort of a yard sale of palladium scrap that sourced that original JM high purity, as they called it, high purity palladium. And what they used to do for the high purity stuff was tap the crucible and pour off the bottom third or so of the contents, and then they take the middle fraction, and that they would set aside as high purity, and then the top fraction, which incorporated a lot of the slag and the liquid boron and so on, they would save that for a subsequent melt. Yeah, so it was a bit hit. The manufacture was, by today's standards, incredibly hit and miss, because they had no XRF or anything like that. Yeah, it was just all depended on the skill of the guy who was standing there loading the crucible. Not many people know that, but say my sister and my brother-in-law both worked there for years, so they told me all about how it was done.
Well, I can help explain why this works and why it's worked in the past, but people didn't understand what was actually happening to the material. But nevertheless, the material revealed by its behavior what was going on. And if you paid attention to that behavior, then you could, by logic, come to a conclusion as to what was causing the behavior. And that's what I did. And that's a somewhat different approach than as most people take in this field.
Yeah, I know it's caused a certain amount of controversy because a number of people are, rather opposed to your idea, but it does, I must say, seem incredibly logical to me that there you have this palladium, and you've even worked out, I think, that the particular size of cracks or dislocations in the bulk metal that help the effect. Somewhat reminiscent, though different in a way, but reminiscent of Arada, who was also very concerned about the critical size of materials. And it seems to me that you've made a step forward in the material science that's going to be of great help to those people who will listen, which is always a problem, of course. But
well, let me add one thing about Arada.
Oh, please do.
Arada and many other people still focus on the size of the particle. He was using nanopalladium. And he had the idea that it was the size of the particle itself that made it active or inactive. What I'm arguing, it is not the size of the particle itself, it's the size of the gap between the particles. And in his case, nanopalladium will sinter very, very rapidly and very easily. And indeed, he ignored that. Makubri, later on, when he replicated Arada's work, opened one of Arada's cells and discovered that it was a solid mass. It was no longer fine particles. It was essentially a solid mass. But within that solid mass were gaps that formed between the particles because essentially nothing was between the particles at one time, and that just filled with deuterium. I believe that those gaps allow the formation of a structure that makes it possible for the energy states of the nuclei to interact with one another. That requires them to get very close together, and that requires the charge to be neutralized by electrons. So I'm proposing that that particular environment allows a structure to form in which the nuclear reaction takes place. And unless that structure is there, that's that then the gap is there, the structure will not form, and you will not get a nuclear reaction. You won't get any heat. That's the secret of the whole process.
Okay, wonderful.
Ed, I'd like you
Sorry,
to talk a
Rebecca.
little bit about how you distinguish this initial chemical situation that then spontaneously goes into a nuclear reaction. You seem to think that this is the thing to focus on first. What is the chemical environment that's going to allow this spontaneous nuclear reaction? Talk about that.
Yeah, that's critical. That's a good question, and that understanding is absolutely critical. This nuclear process occurs in a chemical environment. Therefore, it has to play by the rules of the chemical environment. The rules of the chemical environment normally require the atoms to come together to form a crystal structure. When you look at the crystal structure, the nuclei are little insignificant dots in the center of these spheres that people draw to represent the crystal structure. The nuclei are, from an atom's point of view, an infinite distance apart. There's no interaction between the nuclei. The interaction is all with the electrons. Now, that structure cannot support a nuclear reaction, even though people come up with all kinds of justifications for using that structure as the site, to a large extent because it has an historical support. But that structure simply cannot be it. Nevertheless, whatever structure forms that can support a nuclear reaction, it still has to play by the rules of the chemical environment in which it's located. So I'm proposing that a condition outside of the crystal structure has to form, and that would be gaps. Gaps are a physical absence of the atoms with walls that are containing the atoms that have a very narrow dimension between the walls. And that environment creates a chemical condition that allows hydrogen atoms to accumulate in ways that they could not accumulate when in the crystal structure. Now, this is an assumption. It can't happen within the crystal structure because the rules don't allow it. So we have to have a condition outside the crystal structure. That's an assumption. And then for some reasons we don't understand, the rules change. And the rules now allow hydrogen atoms to come together with a large number of electrons. And when that happens, they suddenly discover that the nuclei can fuse. This is not done anticipating that fusion reaction. This is all part of a chemical system. It's playing by the rules of the chemical system. There's no anticipation that a nuclear reaction can occur. That's a surprise, essentially, to the chemical system, just like it's a surprise to us.
Okay. Go, Ruby. Yeah, you have something else on your mind?
Well, I guess your rationale for this is because you have an analogy that these reactions don't happen in normal materials generally, and they're very hard to happen, right? So that makes
it's hard to happen. They cannot.
They cannot,
absolutely,
and they don't,
because that would violate well understood, very highly supported rules of chemistry. I mean, physicists love to make up all kinds of exceptions to chemistry, and some of them work and some of them don't. But nevertheless, chemistry is an old, well-established, well-understood understanding of materials. And you really need to use the knowledge that has been acquired in chemistry before you start applying physics.
That's right. Speaking as a chemist, Ed, I thoroughly agree. You got me on your side. Now, can we perhaps come to one of the core concepts, of course, I'll mention it before I go on to my question, was the nuclear active environment, those special places within the body of the palladium or whatever other, the nickel or whatever, that actually create the conditions under which this can happen. And it was often felt by researchers that one of the problems that they were facing is that these systems would get so hot, or these places, you know, which they didn't really use your term, they didn't understand your thinking about this, but that when you got a cold fusion reaction within the body of some metal, that it would actually destroy the reaction site. Yeah, and because there would be so much heat and everything, it would just, that tiny piece of the system would blow up and it wouldn't work again. But I think you've actually sort of changed that idea. You think that an NAE, as you call it, a nuclear active zone or environment, will actually continue to produce. Yeah. Am I right?
Yes, and the reason is you really have to look at this process from the atom's point of view. And it's not a gross reaction. In other words, the entire lattice is not being affected. The active sites are individual sites made up of a certain few atoms and a whole bunch of electrons. Those sites are all isolated from one another. Each site fuses, gives off its energy, it regrows, it fuses again, gives off its energy. And so each individual site goes through these cycles. Now, the amount of energy that's given off at each individual site is not enough to do any serious damage. And the reason is that the energy goes off with the particles. The particles have kinetic energy, just like energy is released from all nuclear reactions. The fragments of the nuclear reaction go off and they interact with the environment over a distance. They don't interact at the site. They interact at some distance from the site as this energy is slowly converted into thermal energy within the lattice itself. So each one of these sites gives off this radiation. It's absorbed in a large volume of the material. And so no destruction takes place. Now, if a lot of these sites, by pure probability, pure random chance, happen to be very close together, so that the sum total of all of their energy is too high, yes, then that area can melt, and people have seen the result of local melting.
Got it. Fascinating. The fact that you know the sites can continue to operate actually gives great hope for the longevity of a good functioning LENR system. It's not a flash in the pan. It's not a 5-minute wonder, and I think that's really great. In terms of the outcome, I know you have suggested various outcomes in terms of fusion products, like, for example, a mixture of deuterium and hydrogen will create tritium, which is a tad heretical by some standards, but nevertheless, I'm sure you're quite capable of knowing tritium when you find it in the system. Do you want to comment on this idea of the different products, and have you seen them all?
Well, no, I haven't seen them all. Of course, I've seen tritium and I've seen heat and I've seen electrons. Now, the logic behind my particular model is based upon the assumption that nature has a single mechanism that operates no matter what the isotope of hydrogen is. and no matter what the nuclear product is. In other words, the helium, the tritium, both of which we have detected, both are made by the same mechanism. The question is, what mechanism would have those characteristics that would allow both of those to happen? And there's also a secondary logic, and that is that the environment in which this occurs is very rich in electrons. It has to overcome the Coulomb barrier. And when you have a nuclear reaction, it means that the energy states of the nuclei overlap. They form a common energy state. And since these electrons are there, allowing them to get close enough together for that common energy state to be created, they could be sucked into that energy state and end up in the final product. So I suggest that the easiest way of dealing with both of these necessities,
Good word.
an electron would be sucked in, making hydrogen 4, which is unstable. And I propose that it would decay by beta emission to helium. And so that's how helium gets made. It doesn't get made initially. It gets made by the decay of hydrogen 4. If a hydrogen and a deuterium come together, an electron gets sucked in, and that makes tritium. And if you have two protons coming together, and electrons sucked in, that makes deuterium. So in other words, the process is the conversion of one hydrogen isotope into another hydrogen isotope.
Right.
That's the nature of the fusion reaction. And that is the nature, the common nature. That's the common mechanism. That's the universal mechanism that this particular technique uses.
Right. Okay. Oh, yeah. Thanks for putting that up on the screen. Yeah, I see. Now, you've mentioned many times here electrons, and this brings me to ask you about the interaction you had with Frank Gordon at ICCF 24, and Frank's work and my work too on the lattice energy converter. And I think you have some serious thoughts, and you've been looking into the lattice energy converter. Could I ask you what you think about it and what you found? Well,
Frank and you and other people who have seen these electrons caused the light bulb to go off in my mind. And I suddenly realized, well, yes, that's the way in which this nuclear active state is dissipating its energy. Before that, we knew that ions, ions of hydrogen 4 had to be dissipated when this collective blew up and dissipated its energy. The ions that created the energy had to be dissipated, and those were the hydrogen 4. And I've seen those. I've actually measured those directly.
Right.
But where did the rest of the energy go? And that was proposed to be photons, because people have seen photons, lots of photons being emitted within the apparatus. They can't get out of the apparatus. They don't have enough energy to get out, so you don't see them outside. You have to look inside. But that was never satisfactory either, because you have to have an enormous number, because they just didn't have enough energy individually. When you and Frank saw electrons in large numbers being emitted from these materials that had the characteristics of a source of LENR, all of a sudden, yes, this structure is made of hydrogen and electrons. So what the electrons that make up the structure have to be dissipated and carry the energy away from that structure when it essentially dumps its energy. And my challenge right now is to measure the excess energy and the electron current being generated when the excess energy is made, simultaneously and show that there is a one-to-one correlation between the two.
Got it. Fascinating. That's kind of like wrapping up the parcel wonderfully well, actually. I mean, LEC itself is a bit of a mystery at the moment. There's many things that puzzle me about it, and they're puzzling the hell out of Frank and Harper too. And I'm sure we're all very happy that you've got your mighty brain to work on it too. It's really encouraging to see that there is an underlying mechanism. You mentioned photons, by the way. Jean-Paul Biberian is very keen on the idea that this is photon created by photons, but I'm not so sure. It's certainly worthy of further study, and the more the merrier. Let's study it. But
well, let me add one more thing. You see,
yeah.
In order for a nuclear reaction to take place, momentum has to be conserved.
Mm-hmm.
And people ignore that. For example, if you have the idea of two deuterons coming together to make helium,
Mm-hmm.
that's a two-body to one-body reaction, and there is no way you can balance the momentum.
Yeah.
And therefore, that reaction simply cannot occur. It occurs in hot fusion because when the helium's made, the helium nucleus fragments into two other parts.
Yeah.
Those carry the momentum away. So hot fusion has a mechanism to carry away the momentum. Cold fusion does not. The question is, how's the momentum? How do you get rid of the momentum? If you argue that it's photons have very little momentum.
Yeah.
They have very high energy in order to have enough momentum to match what has to be dissipated. They don't have that energy. So therefore, that automatically makes them unattractive as a mechanism for getting rid of the energy. And that's what caused me to be less enthusiastic about photons. I mean, they were the only game in town, but nevertheless, it was a poor choice. The electrons, on the other hand, have enough mass. And if they are given enough energy, they will have enough momentum. And it isn't just one electron coming off. There's probably millions of electrons coming off at the same time, all carrying the same amount of energy, all going off in all different directions, and all causing the momentum of that structure to be conserved.
Got it. Yeah, the difference there between I think of photons as like BB pellets. You know, there's not a lot of substance to them, but in your analogy, electrons are more like a rifle bullet, aren't they? They've got a lot of energy behind them. Yeah, thank you. Do you have anything to add, Ruby?
I'd like to hear a little bit more about this initial structure. In your paper, you have, you've changed your ideas so much over the last few years, and it's been so exciting to see. In this one recent paper that you have, and I'll just bring up this chart here, you talk about how one of Karabut's experiments supported your experiment with Brian Scanlon later, and led you to believe that what was happening was you were really creating hydrogen-4 as a nuclear product. Can you talk about how this particular experiment leads you to believe that?
Well, both Karabut and my work showed a spectrum like you show there. I also show my spectrum later on in the paper. But that spectrum is, there it is. It is very unusual as a representation of radiation that's coming off of a nuclear reaction. In both of our cases, we found energetic peaks that had a very definite relationship to each other with respect to energy, but also a relationship to each other with respect to magnitude. dropped in magnitude as you went to higher energy, and there was a constant energy between each peak. Very, very unusual. But nevertheless, it's real. Here it's been replicated by two people, independent, completely independent of one another. But I did one more thing that Karat did not do. He assumed that this was helium. I did not make that assumption. I measured the energy, the effect of an absorber on the energy. See, when ions pass through a material, energy is removed from the ions. The ion is not stopped, but it comes out the other side with less energy. The energy change is characteristic of the material as well as the nature of the ion that's going through the material. Hydrogen has an entirely different characteristic than does helium. And I found that these peaks are not helium. They do not have the characteristic of helium with respect to their absorption as they pass through absorbers. They do have the characteristics of a hydrogen isotope. And all the hydrogen isotopes are very similar. So you couldn't tell which hydrogen isotope that happened to be there. And at the time, we had not considered hydrogen 4. So I was thinking, well, maybe it's deuterons. The same spectrum is produced whether you have light hydrogen or heavy hydrogen, by the way, and I can explain why that's true. That's the other support for my model. But in any case, once hydrogen 4 became a plausibility, then that fit very nicely with the conclusions that came from this work.
Gotcha. That I would just mention for the people who are going to be looking at this later, that your Scanlon, the paper you did with Scanlon was presented at ICCF 14, I think. Yeah, and it's available on lenr.org as well, and probably in Jed Rothwell's LENR Canal library too. I read it, by the way. It's a great paper.
I give all the details. You can make your own calculations if you care to.
Yeah, that's right. Okay. I think, Ruby, it's time to say goodbye, actually. I could go on like this for hours. I'm sorry. And
thank you for this opportunity. This is really
Ed,
great.
It's wonderful to talk to you, actually. And Ruby, would you like to wrap up?
Well, thanks, Ed, for your talk at the ICCF 24 Solid State Energy Summit. You can see that talk, search YouTube, Solid State Energy Summit on YouTube, and you'll find Edmund Storms' talk about this new, radically different. Ed, a few years back, we made a movie, and now that movie is completely obsolete, and I'm so happy. I'm so happy. What's next? What's your next experiment? Just to quickly wrap up, what are you doing next?
Well, right now I'm trying to find the quantitative relationship between excess energy and the electron current. And then once I have mastered that, determine the energy of the electrons.
All right. This is great news for a technology. If the LENR reaction can make electrons directly in such numbers as the LEC is indicating, this will really be good news for this planet. So thanks so much. And Alan, where are you going to be found in the coming days?
Well, I'm currently head over heels in the lab, actually, Ruby, and because I have a sneaking ambition, I don't know whether it can be done for all sorts of technical reasons, to build a lattice energy converter that will light an LED. That's it's a big ambition. It may be impossible because they do crackers things like reversing their polarity and so on. Yeah, it's but we'll have a go. We'll have a go. Why not? I've got. I
would give you a little bit of advice about that.
Mhm.
Because the electrons are very easily absorbed by material, the electrons that you're measuring are coming out only from a few microns of material on near the surface.
Mhm.
The rest of the sample is making excess energy. It's the nuclear reactions occurring throughout the sample. And so you're getting energy from the entire sample, but you're seeing electrons only from a surface area of a few microns thick. If you want to magnify the amount of current, you have to make your samples increasingly thin.
Right. Okay.
So it's a surface area.
I gotcha. Mm.
There you
That's
go.
what you call a word from the wise to the apprentice. Ed, thank you so much. Yeah, and goodbye. We'll meet again, I'm sure, before too long. And my regards to Carol too. Yeah. Yeah.
Well, thanks very much. We're going to be posting this on LENRforum.com, so see you there.
Okay, thanks. Bye.
Yeah. Bye-bye.